Just a quick recap. Today we will talk about supervised learning that has a lot of definition. One is this quite famous sentence from Arthur Samuel that is saying that this is the field of study that gives to computers the ability to learn without being programmed explicitly, which is nice, but what actually does this mean? For a supervised task, usually the traditional way in which you can deal with that is that you write the rules of the word, that is your code, then you provide to the code some data, and at this point you get the answers. The supervised learning works in a quite different way. You input the data, you give to the code some of the answers, some of the available answers, and the algorithm finds the rules. Then clearly you can apply these rules to obtain answers on data for which you don't have the answers. But this is the main point. But I want to ask you, I don't need to ask to any of you which of these are cats and which are dogs, right? You can distinguish all of them. But what are the rules? Are you able to tell me how do you actually distinguish cats from dogs from these images? It's quite hard. You can provide overstructure in which you try to mimic what you think that your brain is doing, but it's not as simple as that. And for any attempt to give the explanation, I can find always an image that for which your rule will fail, because your brain is doing something more complex. But still, these images are quite complex because you have animals that are cutted, animals with different objects, different shapes, different colors, different background. Everything is different, but still you are able to distinguish them. And at the same time, you are not able to tell me the rules. And if you are not able to tell to me that I'm a human as you the rules, you are not able to tell to a computer which are the rules. And this makes this kind of analytics quite complex. But the problem is, why do you don't know the rules that you are following? Because you are never been taught to distinguish a cat from a dog with someone that told you a cat is done in this specific way, a dog is done in this other specific way. I don't know the history of any of you as a cat and dog selector, but probably when you were a child, you met for the first time on a book, on television, or directly, I don't know, a cat or a dog, and you ask it to an adult and say, what is that? And your mother say, it's a cat. So you started, identifying a cat with something that is quite specific. This cat is what you know about cats. Then, in the following days, you probably met another cat, and you asked it again, what is that? And someone told you, it's a cat too. Okay, so you generalized this concept. The concept of cat becomes something slightly more complex. And this is the reason for which a lot of children, when they saw for the first time a tiger that usually they saw after many cats, they identified the tiger as a cat too. And one other day, so the boundary of the class cat is expanding. One other day you met your first dog, and you, at this point, you are quite confident about the fact that the dog is a cat, and you say, "Mommy, this is a cat," and no, sweet child, it's a dog. So you starting creating boundaries between the classes. And that's the reason why when you were a child, you had a lot of books with images and with a class, actually. So you learned about the world by seeing examples. The concept of supervised learning is exactly this. Basically, you have a set of examples for which you have something. Something is a measurement that can be a picture in this case, but can be a table. So a list of measures that you have for cat and dogs, star galaxies, or wherever. It's a list of measurement. For some of them, you have also the answer, the adult or the school book, as you prefer, that says this object is a cat, is a star, is a galaxy, is wherever. The aim of the task is to find a function. It does not matter how complex this function is, how nonlinear this function is, but you need to find a function that for at least the majority of the patterns is capable to give you something that is close to the answer that you already know. And you hope, by doing so, that this function can be applied also to points that are different. In the same way your brain did, in the same way you are now able to distinguish a new cat, you want that your method is capable to distinguish a new galaxy, a new star, a new cat, if you want to train that. Basically, this is the key concept of today. Most of the rest of the lesson is boring math, but the key concept is just this. This is what you're trying to do and how you're trying to do. Okay, rules. I asked in the last days to a couple of postdocs to go into surroundings and measuring the heightness and the length of the tails of the animal that walks around in the nearby. Yeah, take consideration when applying for a postdoc here. They come back with this table, which is fantastic. We can all say that the dogs are in the lower right corner and the cats in the top left corner. It's fine. We can build a model wherever it is. I did the most lazy thing that I can do. So I put a straight line on the data, and I say, on the right there are dogs, on the left there are cats. And if you think that this is very lazy, please consider that we actually build most of the empirical law that we know of the universe by using a couple or 3 at maximum variables. And we have lines that separates with boundaries classes using 2 or 3 variables for a very complex scenario. So it's not that bad, a vertical line put there because it's the cheapest thing to do. But no matter that, clearly, when I create a model, I have some failures. So, for instance, there are here points for which the class is wrongly attributed. I'm not saying that clearly this line is the best thing that a human can do. I'm saying that the process that you always try to follow when you are building a classification with some empirical data, it's right there. It's exactly that. You can do that better, but it's what you're doing. The simplest supervised learning method that you can apply is the so-called k-nearest neighbor. That is doing something simple. Basically, you are providing to the code one number, the number of neighbors that you're looking for, and in this case, I selected 5. So I have a mysterious animal because I have postdocs that are not even able to distinguish if it's a cat or a dog. I'm really sorry for that. So I have to classify this new animal, and I try to do that with KNN. So KNN selected the 5 closest neighbors, and the answer for the model is that 4 of them are dogs, 1 of them is a cat. So the mysterious animal, it's at 80% a dog. Just for sake of clarity, most of the models provide you something that is called often probability. Actually, if you met any statistician, this will kill him, because this does not share a lot of properties of an actual probability. So it will be better to say that it's a pseudo probability. But just for talking, given this premise, when I would say that something has a probability to be something or something else, it's a pseudo probability. So statistician can still continue to live. But I can do with this method, but also with most of the other methods, something which is nicer. I said that the model will find by its own way the rules. And this is actually true, because I can ask to the model for each point of the parameter space, what class will be attributed to a point that is there. And the algorithm will answer. And please consider that when you are dealing with a graph, you are able to see 3 dimensions, and you are still that. But this model is capable to do that in as many dimensions as you want. It works in 2, in 3, in 100 dimensions without any problem, and is still capable to provide something like that. The problem is that you are not able to visualize it. But here we have some errors. I put them on purpose because we usually say that the methods are as good as the data that you use to train them. That is true, but it's also nice to understand what can wrongly attributed points, what they can be. Well, they can be a lot of things. We maybe don't have enough data to generalize. Those kind of methods usually need a lot of data, and if we don't have enough data, they usually more prone to errors. This is a possibility. We probably do not have enough features to disentangle the problem. Maybe in this region of the parameter space, it's not enough to know the height and the length of the tail of the cat, to understand if it's a cat or a dog. Maybe we need the weight or some other parameters. It's the other way around of the problem that I mentioned before. As human beings, we selected the rules that we are able to visualize. But it's not given that adding more dimension could not improve the task. Well, there is the possibility that some of the measurements are affected by error, even by large error. I don't want to blame the postdocs that measure that, because it's hard to measure the length of a tail if the cat is not cooperating. But still, this can do 2 things. One thing is that it's moving the point across boundaries. So if the height is slightly less, probably it would be in the other portion of the parameter space. This is one fact. But on the other hand, I have also the fact that the boundaries are built on the basis of the data that you are using to train. So if the training data has a lot of errors, huge error bars, this will become a problem for your training models. And this is one of the reasons for which you need a lot of data in order to marginalize the effect of errors. Besides that, clearly there could be points for which you have a bad label. Maybe for some of them, the method can be right. I find all the time in astronomical catalogs labels that are wrong for any possible reason. Any classification that you are using is affected by errors. It does not exist a pure catalog. There are good catalogs with very few errors, but you could not exclude that there are errors. And again, the errors will come into play in 2 ways. In one way, can affect the way in which the model is trained. But if they are few, you have enough data, this will be minimized. And on the other end, you can see them on this plot when you are validating the method. So you are trying to understand how good is your model. But still, it's something that you have to keep in mind. Clearly, there is the possibility that your model is poorly trained. With trained here, I'm considering a lot of different things. One thing here in this model that has not an actual training, I've selected the number. I've said we choose 5 nearest neighbor. Why 5? I can select 7. 3 is a number, it's valid too. Well, different numbers, these are usually called hyperparameters, will lead to different results. It's not given that anything any possible model with any possible configuration is good for all. Otherwise, I will not teach you more than one model. I will teach you just one model and use that. And for the same reason, I can need a better model. Again, it's with few exceptions, there is not a ranking of good models. There are models that are seeing the world with a different math, so they are creating a different realization of the real world scenario. So you need to try more than one model for identify which is the one that fits better for your case. Just for reference, this model has been proposed initially in the 50s. The current version is more or less of the 60s. And actually, there are some improvements only for computational purpose that have been developed in the last 10 years. And still, even if it's of 70 years old, it's still used. It's still useful. And for instance, it's part of one of the tasks for the derivation of redshift in the Euclid Space Mission. Not directly the derivation of redshift, but plays a role in that. So it's still used, even at top level. Yesterday, Simone and Farida mentioned several possibilities to scale the data. I want to underline that for such kind of method, this is really, really important. We have a small talk with Max yesterday about that. And this is quite important because you are wise beings that you will never perform a difference between something that is in meters and something that is in millimeters. But for the model, the math is really simple. Units does not exist. So if you have something that is in meters and something that is in millimeters, in different columns, of course, the difference if I consider something that is half a meter far in a vertical dimension and half a meter distant in an horizontal difference, in one case will be half of a meter, so 0.5. In the other case, it's still half of a meter, but it's 500. So the distance would be very different. So you can come out and say, okay, it's simple. I don't need to scale data. I just need to use the same dimensions. But it's not even true, because if I want to classify dinosaurs, it is better than classify cat and dogs, I have to say, I can use as parameters the length of the tail and the size of the brain. And even using the same dimension, so for instance, meters, the two sides will be so different in terms of dynamical range that this will not, that will select all the time difference in terms of brain that are closer with respect to differences in tails that are huge. Furthermore, as I said, you are nice guys, and under no circumstances you will ever do the difference between meters and weights and kilos. Okay, but in this case you are allowed to. So you can throw away most of what you've learned about physics. In this case, the concept of metrics, of distance, is only in the parameter space, and it's fine to have weights, because as I mentioned before, it can be helpful to distinguish. So you need to put everything to the more or less same dynamical dynamical range. Yesterday they mentioned several ways. I want to focus two of them that are really often used: the min-max and the standard scaling. I don't need to explain to you again what they are, since they did that yesterday. I want to say that usually they are being selected under different circumstances. For instance, the min-max is perfect when you know the boundaries of a variable. So if, for instance, you have an image that spans from 0 to 255, it's a good idea to normalize according to this span. While if you instead you have outliers, the usage of min-max scalar will put very close all the points of the feature affected by the outlier, while the standard scalar is not. But I want to underline one more thing that is on the right, that those two normalization does not change the shape of the distribution, and this would be helpful for a lot of models. One quite important thing is that you need to be sure to normalize everything coherently. If you have two subsets of data and you start the normalization for one set of data, you need to apply the same rules to the other set. Just as an example, if I have something that spans from 0 to 10, okay, and I apply a min-max normalization, a 5 will be 0.5, clearly. If I have then another data set, the one for which I want to predict the results, and I start, and this will span from 5 to 10 for any possible reason, then I create a new normalization, the 5 will be 0. So it's really important that once you normalize something, you kept let's say, the rules of normalization, and you propagate them towards all the data sets that you're using in a coherent way, or this will be a total mess. I mentioned the fact that if I change hyperparameters, the way in which the rules are built by the model will change. Here I'm considering a k equal to 1 on a data set. You can see this would be called overfitting. We will come back to that, but the result is that will be really narrow around even the single points. It would be actually fitting a lot the noise. I can have an intermediate solution that is 7, and the result seems more reasonable. But on the other hand, the conclusion is not that I should increase this number as much as I can. Because if I select 100, the result is that since there are a majority of blue points, everything will become blue. So on one hand, I have the so-called overfitting, so I'm fitting also the noise. In the middle, I have something that is the best solution, wherever it is. And on the other hand, I come to something that is completely underfitted. So for each parameter, for each hyperparameter of the model, I have to find a so-called sweet spot. I want also to add the small difference. Usually we refer to model parameters to something that the model itself is training internally, and hyperparameters to the one that are on your choice. So you have to deal with this one. There are many ways to find the best solution, but clearly you could not test all of them. This is in principle impossible either for simple models, with the exception probably of KNN. A lot of models have hyperparameters that can span on a continuous range, so you could not test all of them. One possibility is the most naive one. It's check your favorite numbers. So check the first combination, then check another one, then you have an idea. And what if I change these values to this and go further? The second possibility is that is to perform the so-called grid search. So I choose a set of values for one hyperparameter, a set of value for a second hyperparameter. So for instance, for the first one, I select A, B, and C, whatever this means. For the second one, I select 1, 2, and 3. So I check all the combination. So A1, A2, A3, B1, B2, B3, C1, C2, C3. And then I have a distribution of the results. Maybe it can be worth to refine in the surrounding of the result that you think is best for you. But you can even be happy with that. Another possibility that is becoming slightly more popular recently is to going in a more random way, and for a reason. So in this case, I want to test the same number of models. It's clear that if I perform more tests, I have more chance to get the best result. I want to test the same number. So in the previous case, I tested the 9 times 3 by 3. Now I select 9 values of the first variable, so from 1 to 9, and 9 values from the other one that is letter from A to, I don't know, the 9th letters of the alphabet, please. And then I randomly couple those values. So I can have, I don't know, A3, B4, C7, and whatever. Why this could be more reasonable with respect to a grid search? Well, it's not given that all the hyperparameters contributes equally to your task. There are cases, according to your dataset, for which one hyperparameter is really effective in improving the results, one other is not so efficient. In the previous case, with the grid search, I did something systematically, which is fine, but I tested 3 values for the hyperparameter that is more important for your actual task. In this other option, I tested the 9 of them at the price of 9 combination of the other one. Clearly, it's not given that this is better than the other. It's another possibility. You are still testing 9 case scenarios with respect to an infinite combination of possibilities. There are also other clever ways. In the notebook, we added the method that is performing a Bayesian guess. So after the few random attempts, it searches the best solution with a Bayesian approach, but still the concept is the same. Even in this case, you'll never be able to be sure that the solution is the perfect one. No bad news, no good news today. Another key point aspect is the splitting of the data. Why that? If I have a set with the so-called answers, I want to split it. I want to use a portion of the data set to train the model, a portion of the data to validate the model, so in order to avoid overfitting, to see if the model is general enough to to deal with data that has not been seen during the training phase. And with this validation set, I usually choose the best hyperparameters, as we saw before. And finally, I want to have some further points that have never been seen from the model to be sure that I have not overfitted by selecting the hyperparameters. Because even if this is a secondary effect with respect to the first one, so the one in which you are using the same points to train and test, this still can happen. So it's important to have, or according to your possibility, to have that separated. But if you have, okay, so the simplification is that if I trained a KNN with k equal to 1, on the training set, I have actually no errors. There is no possibility to have an error with k equal to 1, because everyone is the closest to itself. When applying to different data, I come with a lot of error, a lot of misclassification. So this is a case of clear overfitting of the first one, and how a different data set can help you to distinguish between one and the other. One possibility, if you have not a so large data set, but it can be used also for other reasons, we will see that, it's the case called cross-validation. So instead of hardly splitting the first part in train and validation, while keeping aside the portion for test, I sub-split this portion in folders, let's say 5 folders, and I use 4 of them for training and the last one for validation. Then I permutate. So I used, for instance, the first 3 and the last one for training, and the one that has been not used for validation. Again and again, in that case, I can use all of that and add something that is more robust, more efficient in order to identify the hyperparameters. And again, I come out with something that is tested independently. But if you are in an even more unlucky scenario in which your data are really few, one other possibility is the leave one out cross validation. In this case, I take for training all the points but one, and I make a training. Then I make a secondary training on all the points, but another one, and I keep going, I keep going. This will let you to have a number of training that is of the same number of your data set. This is computationally quite expensive, but since you are doing that because you don't have a lot of points, it can still be manageable. You had in principle to use a test set also in this case. And this is true. There are some circumstances under which you can not eliminate, I can eliminate the test set because your data are really, really few. This can be done usually under two circumstances. The first one, it's the easiest one, is that since the points are few, I don't want to test hyperparameters. I decide on the basis of something that I did independently with some portion of the data just randomly selected or on a different task, or getting the default values that usually are not so good but not so bad for all. And in this case, the approximation of the N-1 training and the test on the final one is the closest thing to the full training. So it's really close. It's not a theorem because someone argued that exists at least one model that does not, for which this is not true. And it's funny because if you have one model that predicts 1 if the training points are even and 0 if your training points are odd, then N-1 will do exactly the opposite of the full training. For this only reason, this is not a theorem. But anyway, it's funny. You are very boring people. This is the funniest thing that you have in this lesson, so please enjoy it. Okay, I talked so far about classification. All the examples so far aware of classification, but the majority of tasks that we can perform with supervised learning, not all of them, but the vast majority are of two kinds. Classification, that is, I want to distinguish between cat and dogs, and regression. I want to know the temperature of tomorrow in order to decide what to dress. Clearly, this has a lot of application, like the prediction of physical parameters, the distance, for instance, the redshift, and so on and so forth. When I mentioned that we need to choose the best one, we implicitly decided that we want something with less errors. But less errors is slightly vague as sentence. So we should look slightly with more details to the metrics that we can use for that. For classification, every time you perform a classification, this is actually true even not using machine learning, you should consider the so-called confusion metrics. But basically, this is for two classes. In the next slide, we will see how to generalize this concept. It's basically saying, given that one of the two classes is positive, is the class that you are more interested, it's not so important, but consider this as positive and the other as negative. What can happen is that your model is predicting for a point that you know that is positive, is predicting that is a positive. So in the final catalog, since the final catalog will be decided from your model, will be a true positive. If the point is a positive and the model is failing, in the catalog you will have a false negative, because will be negative in the catalog, but you know that it's false. On the other way around, we have a false positive, so points that are negative but wrongly predicted, and true negative. Once you have that, you can build a lot of statistical indicators. The first one, the most obvious one, is the correct points, no matter what the class is. So basically, true positive plus true negative divided by the whole set of numbers. This is easy. But you can also consider something that is specific to your class, and that this is something that you may be really interested to, depending on your problem. For instance, you can consider just the horizontal line. So from the number of the points that are positive how many of them will be in my final catalog. This is usually called recall or completeness. There are several cases in which you can be interested in maximize the completeness. For instance, for rare objects, or if you are managing a nuclear plant, you want to shut down it in any circumstances that will prevent an explosion. So you prefer to shut down it one time more, but do not have any possible explosion in your nuclear plant, usually at least. The other possibility is to use the columns rather than the joke on the model before. It was way funnier than that. The other possibility is to consider the column. In this case, we are looking to the points that are being flagged by our model. So in the final catalog, that will be positive. We want to know how many of them will be actually positive. So I can divide the number of true positive plus the sum of true positive and false negative. This is usually called or precision, or in astronomy is mostly used purity, because we know that in the end we will come out with 100 candidates from our models, and we want to know how many of them will be actually of the proper class. For instance, if you are planning for a follow-up, you want an high purity. You prefer to lose some of the points, but the points that you're using to point your telescope should be mostly, at least, of the correct class. You don't want to waste time. Furthermore, there is the F1 score, that is the harmonic mean of purity and completeness. This is for two classes. The generalization in n classes, it's quite simple. You go back to the two-case scenario. So for each find purity and completeness, considering all the other class as one. So they been together, and then I move class by class. Besides that, I can micro and macro average the results over the different classes. This will take or take not account of the relative weights of the classes. So if I want that a class weights 1, no matter if it's composed by 10 points, or if I want to multiply for the number of points. Both aspects have pros and cons, depends on your task, how much you are interested in a class, because the unbalanced data set can be tricky. A further bad news is that you can always optimize your method on one single indicator, obtaining a dumb model. Because in some cases, there are dumb solutions that works really, really fine. For instance, if I have unbalanced classes, having something that says always that is negative prevent the model has a huge accuracy. Or I can obtain a paranoid model that says always that is the true class. In that way, I have the 100% of recall. Clearly, everything is of the positive class, or there are the timid model in which I obtain a really high purity just because it's selecting really a couple of points. All these models are useless, mostly, and can be a trivial solution for the optimization. This means that even when you are interested in one of these specific parameters and you are trying to optimize on that, please be aware to look at all the others, because this can be important. Let's come back to the pseudo probability. So the statisticians are fine. Most of the model, not all, but most of the model has this kind of possible output. So far, we considered the so-called winner's take all. So if the pseudo probability is slightly more to be of one class, no matter how slightly this is, this will be attributed to this class. So in a two-case scenario, the winner will be something that takes 50. So from 0 to to 50 will be class 0, from 50 to 1 will be 1. Clearly on the boundary, there is the 50 will be on the one class. This is fine. This works quite well, but if you want to optimize something, for instance, for purity or completeness, this is not given that is the best solution for your problem. You can change this threshold and do something slightly different. For instance, if you're interested in having a high completeness, I can move the threshold, in this case to 0.2. That is probably too much. This will push the completeness to a higher value at the price of a lower purity. This will change clearly the confusion matrix because it's the way in which it's produced. On the other hand, I can select a higher threshold. This will lead to less completeness and more purity. Again, it's on you. It's something that you still need to do on your validation set, not on the test set. Otherwise, you are fitting way too much this effect on the test set. There is a possibility to encompass all the possible outcomes of all the possible thresholds in just one plot. This plot is called the ROC, and it's basically considering on one axis the recall of the positive class, on the other axis 1 minus the recall on the negative class. Don't ask me why they chose that way, but it works. Practically each point of the line, it's a different threshold. So you have all the possible combinations, so you can even select the balance. So if I find something that is going on an horizontal branch, this can be a quite good sweet spot to choose your parameter. But it's also saying how well the model is distinguished the two classes. The ideal case scenario is that your model is really confident, and for each point of the class 1, it's saying that is 100% class 1, and for each point of the class 0, it's 100% of class 0. This will lead to something that looks like that, and therefore there is no threshold that could change the results. So I will have an horizontal line. It's the perfect scenario. In this case, the area under the curve will be exactly 1. And the worst case scenario, a random guess will be, will have a random, an area under the curve of 0.5. So I can use this area in order to understand how well are separated the class for the model. It's an overall measurement that does not exactly answer to your task, but it's saying how good the model has been trained, and it's quite useful. I mentioned the fact that if we have unbalanced class, this will lead to a huge sort of problems because all the models will probably push for the majority class, because optimizing it to have a proper answer on the majority class will give for any possible indicator a good result, will push it up. So the optimization can be harder to be found. So there are several strategies to minimize this effect. If you have a lot of data, one possibility could be to decimate the majority class and keeping less of them. This is a possibility, but often you don't have enough data, at least not as much as you want, so you probably don't want to do that. And especially for rare objects, for instance, for a strong lensing candidate, often the other possibility is to add simulation, but you need to trust the simulation a lot. You need to really trust them a lot. Another possibility to use is to create synthetic data from actual data. It's a strategy that is called SMOTE. Usually takes 2 points and takes the points that is on the connection between the 2 points of the minority class. Again, this can lead to points that has no physical meaning, but can help the algorithm. The only answer is in the test set. You can try wherever you want up to the validation test. Then you move to the test set and you discover if your strategy is improved this result. Besides that, but this is model dependent, there could be the possibility to adjust the method, suggesting to the method that you have a minority class and you don't want to lose it. So different method will push the minority class according to the relative weights present in the data set. Not all the methods give you this possibility, but some of them did so. In this case, it's usually better to use this possibility if it can be selected. Regression metrics is quite simpler from the point of view of the metrics, because we always take into account errors and so the difference between the predicted values and the expected one. And usually, if we take into account the 4 main modes of the Gaussian, so mean, standard deviation, skewness, and kurtosis, we are almost fine. But I have to say that specific domains can have specific requirement. Since I worked for more than 10 years in the derivation of photometric redshift, I know perfectly that for them, it's important to normalize for 1 plus the actual value of the spectroscopic redshift. But this is something related with the domain, so I could not give you suggestion besides read the paper of your domain before perform a metric. So I will move to the second model of today. So far, we considered on everything the poor KNN. So if you have some questions on this key concept, you can, please.
Thanks, Stefano. Very dense of information. So just to have a confirmation of what I was thinking, imagine that I have a set of parameters to distinguish between cats and dogs.
Yeah.
Using them simultaneously is not the same as piping the different criteria that I could use to base it on these parameters.
It's not the same. It depends on the model, of course. It's not the same, and it's not guaranteed that using all of them, it's the better choice.
All right.
The world is really a bad place to live.
So basically, it's driven by your problem. So to use the ad hoc solution.
Yes, identify the best parameters in terms of feature of measurement for your problem. It's a quite important task, because in the best case, you are wasting just computational time on something that you will not use. But in a lot of cases, this will lead to the decrease of performances of the model itself. I will show you that slightly more on Friday. But already Simone mentioned that usually classifier adding features, just by adding features, improve at a certain point, and then you will see a decrease. Every time you add a new feature, you are adding more information, which is fine, but at the same time, you are making the world more complex. So identify the best solution, and in particular, for models that try to find a lot of hidden parameters internally to fix the solution, will lead you to the possibility of falling in a local minimum. So the model at a certain point is convinced that I could not find anything better than this, and still is stuck there. And there is also a geometrical meaning for that, if you want. Basically, we consider as better sampled the points that are in the circle inscribed by the square of your feature. because you have not points on the outside from the corner, so the points on the corners are less sample because they are less dense. Okay. The ratio between the circle, then the sphere, then the hypersphere, the ratio of the sphere with respect to the hypercube is going to 0 really quick. If you did the math of the generalized n-dimensional figure, this is going to 0. So all your points basically are going to corners, to n-dimensional corners that are hard to be imagined, but still there.
Thank you.
Any further question, or we can go to decision 3? Decision 3. Okay. This is a flowchart model. Basically, it's doing something really simple. Start from one point, you have all your points, you ask a question to your points. Who is older than 40? Then the people older than 40 go on the right side of the room. The people younger go on the left side. Then I go to the right side of the room and I say, who is taller than 2 meters? The people taller than 2 meters can go in the upper part of the right part. The people that is smaller here. Then I go here and I don't ask the same question. I ask another question, whatever it is. Who is dressing something red, go in the upper part. Who is dressing something not red, going in the lower part. So it's subdividing, and subdividing. And this is basically how the method is done. The trick is how to do that. In the end, there is an optional part in which I can cut completely a tree because of some statistical indicator, but since it's not really used nowadays, I will skip this course. Just say that it's possible to prune the tree, because we need to have an actual word for this. There are several kinds of split. Clearly, the concept of dressing red, blue, green are nominal values that I could not actually group. I have two possibilities of saying red versus anything else, or I have to select red, green, blue, and so on. I have some categories that have an ordinal value. So, for instance, small, medium, and large. So I can split in more than one way. I can split small and medium versus large, or medium and large versus small. And clearly, I have the most typical variables that are just numbers for which any possible question is fine. So more than 2 meters is fine, but also more than 1 meter and 99 is fine too. The point is how to split. And the answer is by asking all the possible questions. I mean, I can introduce an information criteria on your data. One of the most used is the entropy. The formula is there, and is basically obtaining a value of 0 when a class is completely pure. So if I have in the room all people of the same class, all cats, the entropy will be 0, while if I have exactly 50% of cats and 50% of dogs, the entropy will be 50. Will be 1, sorry. No. The idea here is to measure this value before, then measure this for the 2 branches. So after I subdivided it with the first question in the right and left side, I can measure the entropy for both the subsets, and I can weight them in order to assess if the entropy is improved or not. Then I basically ask all the possible questions on all the possible variables, and I choose the best question. Then I can move further. I mentioned in the bottom part, the Gini index, although it's less popular, is the default value for random forest, so it's quite important. The concept is exactly the same, it's just slightly changing. The perfection is still 0, and the average is 0.5. In this case, the name is not a word, it's the name of the actual guy, Mr. Gini, that proposed this indicator in the 80s in the 1862 or something for economics. But it became popular for machine learning 100 of years later. So in this simple case, I have the mixed, I have 15 points for both the cases. If I cut vertically in the two portions, I still have two boxes with 15 points each. Each of them, if you do the math, has an entropy of 0.35. When I weight them, because I'm lazy and they're exactly of the same number, this will lead to an average of a weighted average of 0.35. So I improved the entropy of the overall data set with this split of 0.65, and it's fine. But what I have to do is basically what I say, that if I have this data set, no? Okay. I test by student. I take this example from the web. I test by student, I test by age, I test by credit, and I get 3 different values of information gain. The best one is the student, so I keep that, and I go to the branch in order to subdivide it and see if I'm able to improve again and again and again. This is the key concept. Clearly, this model is not affected by the normalization, since as we say, standard scalar and min-max normalization does not change the shape of the distribution. In this case, they don't give to the normalization, because they just need to find a threshold to cut, and it's always the same. And clearly, on the other way, if you want to predict, you just need to follow the workflow. This is also informative because you can actually follow the workflow. You can see how precisely your method predicted if something is of one class or the other. I can use it as a classifier, but has been modified in order to be used also for regression. All I need to use is something that gives me the concept of entropy, that can be the standard deviation. A more compact subset, it's better than a way larger subset. So I can work also for regression. I forgot to mention that KNN can be used too for regression by just considering the mean or the median of the neighbors as your prediction. This method has been proposed almost independently in the 80s by 2 independent groups that are slightly different, but the concept is exactly the same. This model is quite prone to overfitting for how it's built, and it's not so popular, but I showed that to you because it's the base of a very popular method, that is the random forest. Basically, here we are creating a forest of decision tree. So hundreds of decision trees, and we will use them for the final classification or final regression. But for what I told you, you know that decision tree have no randomness. So if I take the same data set and I create 1,000 decision tree, they will be exactly the same, because they will pose the same question at each level, so they will be built in the same way. Leo Breiman, that was one of the proposers of the decision tree actually, proposed a 2 layer of randomness here. The first layer, not all the trees, we will see a different subset of data. Yes, please.
No, it's just before we go to random forest. It's looking at the decision. I never use decision tree, but looking at the decision tree, I work with asteroids, and we are always obsessed with looking at the small classes. That's the obsession of asteroid people. And I think decision tree is a good choice to initialize supervised and unsupervised methods. Could I say, at least, okay, I say how is a S complex type asteroid is, how I see complex type asteroid. There is characteristics that set them so differently that at least I can do that to start something. Is it a good way to do it?
You are not forced to use all the possible data in the world to train a model. So if you can split your data set in something that is more compact in all the possible meaning of this word, you can create two independent models, just one for each class. But in the end, the important thing, the very important thing is when you get a new single point, can you attribute to one model or the other at first? Because if you, if I have a galaxy and quasars, just for instance, and I want to to predict the redshift for galaxies and quasars, it's fine, and it actually works better. But then I need something at the first step that tell me it's a galaxy or it's a quasar. Can be a machine learning method, can be a flag that you are already completely aware of it, and so on. The important thing is that if you split something, then in the real world application, you need to split it at the first stage. So if you can do that, yes, it's fine.
Okay, thank you.
Unless, well, if one class becomes of 3 points, then there is few things that you can train on 3 points. But I mean,
like SDSS colors, basically, like 4 points or 5 points. Generally, it's like that.
Okay, so the two layers of randomness proposed by Breiman are to not provide to the different trees the same data. So each tree is exposed to a subset of the data with some of the rows that even be duplicated. This is actually an option, but often they are used in that way. At each node, a tree does not see all the variables. So we are building a Platon of stupid trees that are dumber than how the original decision tree can do, and they are way better. This is so sad to say that a Platon of dumb trees is better than a wise one. But in the end, we will proceed through all the decision tree, and then we will vote if we are going to destroy Saruman or not. This is how the method works. Basically, it's exposed to a different portion of information in both sense, vertical and horizontally. And still, they are able to vote in the same way. Basically, just for recap, if the original data set has R 1 to 5 points and 4 features, in the first step, all the trees will be exposed to different subset of rows, then the tree starts. And for each node, only a subset of the features will be proposed to the node. Then let's vote. And the majority wins. Clearly, again, this is true also for regression, where you can use the average or the median for the final assessment, and you can go that way. I didn't mention this kind of algorithm, both decision tree and random forest can be balanced for class that have a minority, since when I will calculate the information gain, I can use different weights to push for one solution or the other. Of course, all right. Well, 3 trees is not, it's funny to say, but it's not a forest. So it's just for visualization purpose. This algorithm has been, I don't know why, there is also Tim Caho in the slides. I don't know why she is missing, I'm sorry. It's been proposed in the half of the 90s, but the version that everyone uses nowadays is the one from Leo Breiman from the start of 2000. Oh, here she is, sorry. This model, it's really used also because it has something completely built in. That is the feature importance. Since we can go through all the trees and verify when a feature is chosen and to select how many objects, I can go through all the trees, average this, and come out with something that gives me the hint of how much a feature is important for the task. And this is really useful for 2 main reasons. The first one is that allows you to understand better your problem. So clearly it can come out with something that you already expect, and this is fine. But you can suggest something that you are not aware of. And the classification can be, this can be interesting from a theoretical point of view. At the same time, if something is really, really strange, is something that you completely do not expect, this can be a signal that your data has something wrong, or that there is some circular loop in your data. For instance, if you're creating your class using, I don't know, radius more than 0.5 or less than 0.5, clearly, this variable, if presented to the method, will lead to a great result because it's a simple cut and it's fine. But in some cases, this is slightly trickier than that. And some correlation that you should be aware, but maybe are hidden in the description of how the label are built in the survey, this can be spotted in that way. If you find something that you completely do not expect, there is the possibility that you are winning a ticket to Stockholm, but I would say that there is some problem in the data that should be addressed at first. Clearly, this is not the only way to do that, to assess the importance of the feature. There are some of them that are even model agnostic. For instance, you can take your test set, shuffle the values of one column, and see if the results become worse. Hopefully they become worse, but if they become really bad, this will mean that the feature is important. If the results are quietly the same, probably this feature is not being used anyway. In the second session, we will see also a method that can tell you something slightly more than that. The next method, the final method that I want to present you today, also because I'm probably late, are the support vector machines that were originally conceived to separate classes in a linear way. So basically, the target is to find a line in 2 dimension, a plane in 3 dimension, an hyperplane in n dimension, but let's go for 2 dimensions just for visualization purposes. In 2 dimensions, you are searching for a line that is splitting the 2 classes. So for instance, the green one here is not splitting anything, but the blue and the red one are performing the task. There is a huge bunch of lines that can do the task. So support vector machine are trying to maximize the margin between 2 classes. And to do that, they select some of the points of your dataset as support vectors. They are the boundaries. So the idea is to find the maximized distance between the 2 boundaries of the classes. The bad news is that even 4 points cannot be separated through a line in all the condition in 2 dimensions. So the algorithm need to be generalized to do something different from that. The idea of the support vector machine is to use a kernel function to create synthetic new dimensions that are dependent in a very nonlinear way, hopefully, from the other that you have. So you move, for instance, this circular class surrounded by another, surrounded by a ring, another class, in a 3-dimensional space where I can find a plane that cuts the 2 classes. And then I can reproject on the original dataset and found a circular separation. But the problem geometrically have been addressed maximizing a linear separation. So it works quite well, and in principle, by going to an infinite set of dimensions, any problem with that does not exist two points that are exactly that have exactly the same values but different classes. If those couple of points does not exist, it will always exist a solution to the problem. It's not given that this solution is meaningful. Probably this is hard overfitting, but theoretically it exists. I mentioned that there are several kernels. Of course, the linear kernel is practically helpless. It's just for visualization purposes usually. So you can use polynomial forms, the radial basis function that are quite used, or sigmoid. Actually, you can build any possible function that you want and apply it. Usually those are the most used in this work. Here, since we are talking about a vectorial product between the 2 classes, the normalization will matter a lot. So it's better that everything is normalized, possibly with the maximum of 1. Usually for support vector machine, it's still better to have something between -1 and 1. But just to visualize what the result will be, taking this simple data set for which I have 15 points and class 1 and -1, different kernels with different hyperparameters will lead to quite different solutions. The points that are circled are the one that has been selected as support vectors. I'm saying that because a large number of support vector usually is a sign, not it's just a clue that the algorithm is going in overfitting. Because in principle, a solution with all the points as support vector is clearly overfitting. So the linear one, even selecting all the points as support vectors, is not capable to distinguish anything. And then different kernels with different hyperparameters will lead to different solutions. In some cases, really different solutions. So again, it's really important to use something independently to assess which is closest to the reality. Because you could not choose among any of them without a different solution, without some external data. Among the parameters, SVM has several of them, something related to the kernels. There is one that is usually really important. It's the penalization parameter. It's a parameter that suggests to the network, to the support vectors, how they can be accommodant. They can consider a margin in which the points, if some points fall there, it can deal with that. I can accept that, it's fine, stay there, I don't care. This is useful because a very strict margin, although it's going to obtain a really precise solution, is often fitting also the noise, so it's usually it's in overfitting, while on the other hand, having something really, really wide will lead you to underfitting. And those are continuous values, so the possibility to find the real perfect solution for your problem, it's quite complicated. Welcome to the real world. These have been modified. I say that is for classification. They are being modified. They are not so popular, but can be used for regression. The idea in this case is to create an hypercube surrounding your data, and you're performing the same trick. You are trying to find the hypercube closer to your data that is capable to enclose all of them. Again, changing the kernel and changing the hyperparameter will change a lot the shape of your solution. Clearly here we are looking into something that is bidimensional, and it's quite clear, and still without any further point, you don't know if the polynomial of the 10 degree or the radar-based function is the best solution, and still they are quite different. In this case, the parameter that allows you to tolerate some errors is named epsilon, because it was too easy to have the same name to two parameters that do exactly the same thing. But still, the concept is the same. You can see, in particular on the polynomial, there are wider boundary allowed for to the network. Those are being introduced in the 60s, even though the current version is mostly from the 90s, and they are still quite used. In chemistry, they are really used for in order to identify the best solution for drugs. I don't know why, but they used that a lot. Probably they started using them and they never moved on. The quick recap is that despite some pros and cons of the different models, for instance, K, it's quite understandable. It's fast because it doesn't have a training. It's slightly slow on the prediction, but still manageable. The random forest does not need the scaling and provides you the feature importance. SVM are quite effective for a lot of problems. Still, they need a lot of optimization. The final answer is there is not a better model for all the problems. So the idea is to try several of them with several parameters and try to find the less worst solution, at least. I want you to come back to the idea of the rules from which we started, just to see how different is the world as seen from different models with different hyperparameters. So the first one, it's the KNN with just 1K. You can see how it's creating islands all surrounding any single points, while an intermediate solution is finding some reasonable boundaries, and then instantaneously they are dropping the gulf there. A decision tree that can go as deep as you want, create some weird structure. Please remind that the decision tree will ever produce surfaces that are rectangular somehow, because it's the way in which it's cutting the parameter space. And then it's performing something. The last one, it's if I force the decision tree to go as deep as 1. So it's just one question. So the only thing that can do, it's an horizontal or vertical separation. Random forests are doing something slightly different. The first one, it's just with one tree, so it's another decision tree, but it's a dumb decision tree. And in fact, you can see that it's quite stupid. Then the other one seems to be more robust. Here I'm changing just the number of trees, so apparently the last model seems to be slightly better. An SVM with a linear kernel, it's stupid as it can be, while the other two solutions, in particular the one with the hard margin, it seems strange. But still, it's reproducing really well the model, but we don't know if the corner, for instance, is reasonable, or is something that, where the fudge? Okay. In the top left corner of the low right image, there is a orange region, and you can only test if this is reasonable or this is an artifact of the model, of the way in which the model has been trained. But by quoting Linus Torvald, we will move to how things are done. Before the coffee break that you surely deserve, I want just to show you how simpler are some of these things. For instance, we have libraries for which the split is done just with one line, also forcing the class to be stratified. The standard scaler is one line for fit and one line to apply the scaling to other points. Please, again, never train 2 times the scaler. Train once and apply it to all the other ones. Initialize a model, it's just one line, so you are declaring which is the model, and the hyperparameters that you want to use are there. Then you can fit it by providing him the features and the labels, and then you can predict, and you have also models that provide you most of the metrics. Also, the grid search is quite simple. You need just to define a dictionary of the values that you want to test, and then say, I want to test this model with this param grid, with a cross-validation of, for instance, 5, and my target is F1, for instance. But I can select another metric to be optimized and get back the best estimator, and finally obtain the prediction and the confusion matrix, and so on and so forth. We will see that better in the second section. If you have any possible question.
Sorry, I'm boring a lot, all of you. I was just wondering if from the mathematical point of view, if you, for example, you go back to your problem to disentangle cats from dogs, and you have a set of parameters, if you are able, or you're in the position to find a combination, a linear or nonlinear combination of parameters, so that you can easily put all the cats on one side and dogs on the other side. I think this is a kind of orthonormalization process.
You can always, for any possible question, when in the question there is the word always or never, the answer is almost all the time no. There are highly nonlinear problems for which this could not usually be done. For instance, one example is the example that I used with the cluster of points surrounded by a ring of other problems. To put them on one side or the other, it's what the support vector machine try to do. Is exactly that. They are creating a high nonlinear combination of parameters. After that, an hyperparameter is capable to cut them out. But it's warranted that this is actually what you want to do. It depends, because it can be hardly overfitted. But from a certain point of view, it's what SVM do. The idea is exactly that. I combine them in a very complex way, then in something that is quite hard to be understood by a human being, they are separable with the high-dimensional hyperplane.
Just for example, think about the equation of the fundamental plane of galaxies.
Yeah.
And you are combining different physical parameters, but at the end you have a straight line. This is the point.
You can trick with you can cheat in a lot of model or a lot of things. It's not always a good idea to go back to something that is human completely visualizable, because we are really bounded by the fact that we are able to see 3-dimensional at the best. And well, we can cheat, we can add colors, we can add signs, we can do a lot of things that suggest us something, but if you force something to go back to 2-dimensional, TSNE, for instance, do it really in a really good way, but still it's a compromise. The truth is only in the complexity.
Hi, and going back to application, so going back to my case, like
Okay. No,
S-type asteroids, C-type asteroids, and if I have to do, like, I know nothing, I'm a newbie, and I will go straight for the random forest, I suppose. If you had to tell me, Pedro, application start with, because what I see is that from what you showed us in the example is that if I go from from one tree to like 100 trees, it's, I mean, the space, it seems more robust and stable than the other ones.
well, usually more trees, trees, it's something that you can always expand. So with respect to other parameters, the number of trees, it's something that you can always add. Please consider that the computational times is directly proportional to the number of trees, because training one tree is, if training one tree takes 1 second, training 1,000 trees takes 1,000.
But what I mean is that if for the case of random forest, I have less chance of making a wrong choice of tree.
No. I just selected. I'm plenty.
Can be worse.
I'm plenty of things that I can do. For instance, all the criteria that comes from the decision tree. How many questions? How many deep can be the decision tree? It's a parameter also for a random forest. When I want to stop the criteria, if I want to go up to leaves with just one object on that or more, I can change. Well, I can change between entropy and Gini. Yes, they are a method that works quite fine even with the default values. You can enlarge just a bit the number of trees because it's funny, and usually improves substantially in some cases the results. I have to say that after a certain point it's meaningless. But
that's good.
Yeah,
that's good, because then if I'm training something, I want to see something fast. It's quite good that the parameters at the end don't.
They are quite stable. In fact,
so
they are quite used. As you said, from noobs, they are quite effective, and they provide you feature importance that is interesting, and so on and so forth. But still, you can mess also with them.
Yeah, no, sure.
There is always the possibility to mess with.
Yes, I suppose. Thank you.
You're welcome. No,
thank you, Stefano. Beautiful explanation, beautiful lesson in general. While for me, it's really clear all the method in terms of classification. Also, the example is very straightforward, the cats and dogs and the separation of the hyperspace in different regions. Can you spend a few words about the application of this method for the regression? Because if my problem is, I want to predict, I have this kind of data, I want to predict, for example, what will be the temperature for tomorrow, let's say, how this system work in the end. I understand that in the end, you try to separate your plane and then you use the average or some quantities that you compute in single regions. But if you can do some example how you can use this, it would be very useful.
I can do that for all the single models. Let's start with the KNN. KNN is selecting n neighbors. Each of them has enclosed the temperature. So I select 5 neighbors. the 5 neighbors have temperature T1, T2, T3, T5. Then I can or choose for the mean or for the median. And then I can also attribute an error using the standard deviation, for instance. Okay.
That will be the properties of that cluster, okay?
Yeah,
right?
the idea exactly this. The idea of most of the machine learning methods is that points that are close in a parameter space are similar. Practically everything rely on that. If you are assuming that if they are close, they share the same class. If they are close, they share the same value of something. This is the main idea. You need to choose properly the variables and so on and so forth, but this is the idea. So for KNN, it's exactly that. So you select 5 of them, average or median, plus the standard deviation. For a decision tree, in the training phase, you use the standard deviation to select compact leaves at each step. I want the group of points to be as compact as possible in the variable that I want to predict. So I want, I don't know, no matter what is the question, if the label is the temperature, I want that all the points with the temperature, I don't know, 10 go on one side, or about 10 go on one side. The one with temperature 40 go on the other side. So they will be as compact as possible. This is the minimization that I want to do. And in the end, when I follow the tree, I will end in a region according to the stopping criteria that I choose for the tree with the bench of points. And again, there I perform median or mean. Clearly, you can use also other statistical indicator. You can, I'm saying the standard one are mean and median, but clearly you can use whatever. And again, closer with them, you have also the standard deviation giving an hint about the error. Clearly, a random forest is the average of the averages. So you have a probability distribution function, actually. You can build the whole distribution, and you can also see if it has more than one peak. That could be interesting because you can have secondary results that should not be suppressed. This is particularly true. I'm probably boring people, but it's particularly true when you have subclasses. For instance, if I have photometric redshift, I have what I've done for 15 years or something. You can have subclasses that are less numerous in the data set, so they are less. If they are similar, because there is a degeneration in the parameter space due, for instance, to moving at different redshift of the Lyman alpha or the break at 4,000, you can see the 2 peaks of the 2 solutions. And if you consider always the peak, you are pushing toward the class that has a larger value. If you include all the solution also with the secondary peak, you can come out with a distribution of distances that takes into account also the minority class. So it's quite useful also to have this probability distribution function. For SVM, as I shown, it's trying to do actually something different. They are trying to, it's not an adaptation with the mean of about something. They are performing an actual prediction based on the hypercube. So there is more specific. But those models works in this way. For neural networks that will be shown by Giuseppe this afternoon, it's again a different way. I was not supposed to give this lesson today. This lesson was supposed to be done by Alexandra Adveda from the Observatory of Archetri. But since she could not be here today, I basically replaced her. But she already prepared another book, and she did a great job. Then I take the the great notebook, and I butchered it because I want to change something because just because for fun. And so whatever you find in this notebook, if it's something really well explained like a book, it's our credit. Wherever you find something that is not so clear why it's in this weird way, this is my fault. Just as legend to read the notebook. As I said, I want to go as quick as possible. The notebook is supposed also to be like a sort of cookbook in order to perform several things. It's quite commented, it's quite clear, her credit again. But I want you to perform the final exercise. The dataset that she selected is an air quality dataset that was originally meant to be for regression. I will not go into the details. For what we are interested to, there are some variables and a class that she converted from a regression problem, so a measurement of the quality of the air, to a classification problem, just creating two classes. It's good, medium, or bad, connected to the air quality. So she loaded the data set. Here there is also all the explanation about the train test validation that we had in the past slide. In that sense, I said that this notebook is a good cooking book. Her credit again. And basically here she just loaded only the feature that we want to use for our experiment, not all the other ones. And also clearly she loaded the classes. Those are the numbers that we obtain, and then we can finally split the data set in train, validation, and test. The function that we are using, it's train test split, as you may notice, does not include the validation. This is due to the fact that in a lot of cases, we will use cross validation, so it will be embedded in the training set. But if we want explicitly obtain a validation set, we can do this in two stages, basically. So it's initially starting splitting, obtaining an X temporary and an Y temporary, and the X test and Y test with a test side of 20%, 0.2. Then, with the remaining 80%, I take 25% of this 20, and I get, so 20%, 25% of 80%, it's again 20% that is for validation. So I am applying basically the same method twice. And I have, so the feature for test, the feature for train, the feature for validation, and the connected labels. And I can print the numbers, of course. It's again explained why the validation is needed and so on and so forth. I skip this because we just talked about that. Again, the cross-validation and so on. And here we are talking about the scaling. So here is creating a standard scaler that is a method from sklearn, and it's fitting and transforming the data from the training and obtaining the scaled feature. You can also only fit the data, but usually it's easier and faster to do both the tasks at the same time. Then, without fitting again the scaler, we can transform only the validation set and the test set. What we can do is perform an experiment with unscaled and scaled data. So I'm declaring a KNN as classifier with 10 neighbors. I can fit the model with the train and test, and then ask the score for the model on the validation set. And I can print it, we will see the result, and I can do that the same thing on the scaled data. And then the results are basically that. So I can obtain an accuracy that is slightly worse for KNN. Clearly, how worse it is, it depends also on the distribution of the feature that we are actually not looking at all. While if I perform the same experiment using a decision tree, here the decision tree classifier has been created with a max depth of 5. You can see that the accuracy is exactly the same, because as we mentioned before, the decision tree doesn't care about the normalization for the way in which they are created. So I can use this classifier to predict the values on test scaled, and we can see which is the output of the scalar. In this case, is specifically 1 or 0 for all the point of the test set. But I can also ask for a predict underscore proba that is actually answering with the probability to belong to each of the classes. So in this case, you will see that y pred proba, I should select better the name of the variables when I have to pronounce them, but no matter that, here we have the probability, pseudo probability, please statistician, don't be mad at me, for belonging on the first class, and then the probability to belong to the second and the third class. The sum is supposed to be 1. Since here we have 3 classes, we can see that, for instance, the first point has 0. We could not see the second class, and it's 3 for the third class, while for the last point it's 0. It's 0, 0.9 and 1, depending on how do you print them. The sum is 1. So this is the probability to belong to each of the classes. Here is the recap of the confusion matrix, accuracy, precision. As I said, she did a great job. It's something that I would never done for that. And we can build here a function that is just for avoiding to ask to the model again and again and again for all the notebook to do the same things. So it's practically performing the prediction, sort the variables, and print out all the statistics that we are interested to. So accuracy, prediction, recall, and F1 score. So it's basically just that. So we can now again train a model. I can even use just the model trained once, but it's just for repetition, and then evaluate the model with the function that we just declared. And so we have all the metrics. What we can also do in this cell, most of the code is just for producing the plots, but this is stupid. Okay. Here I have a KNN with the number of neighbors selected in this way, and we can see the considering with respect to the good class of the 3 classes that we have, the ROC curve and the confusion matrix. Here we have, for instance, a 98.9% of the area under the ROC curve using k equal to 10. If I move the slider, and you can move it too, this will change. So here, for instance, the confusion matrix is changed, the shape of the probability, pseudo probability, it's changed, and the area under the ROC curve is slightly decreased. But if I push this value quite far, you can see that the confusion matrix is becoming worse and worse. And also I had a further drop in terms of the ROC curve. And finally, if I push toward the limit, so the number of objects is predicting everything as bad. There are no score for good and so on. So I obtained a complete underfitting. On the other side, using just 1 as for reference, this is where I will get. It's not even so bad, but still it's way worse than what we obtained with the 10 or any in reasonable value. I can do the same job with a decision tree. Here, again, all that we need to do is create the object of the model, give the hyperparameters to the model, and then fit it. Then we can evaluate the results and see what's going on. So a different confusion matrix will be produced. I'm going as quick as I can. Moving to the hyperparameter, here there is also a list of the parameters that we can pass to the random forest. Here I'm considering a grid search. As we mentioned before the coffee break, I created a dictionary with the parameters that I want to use for optimization and the values that I want to use. So since we will use a grid search, we will obtain 16 attempts with all the combination of those parameters, and we can obtain this. This is a chart of how the F1 score is coming with the different values of depth and different values of number of trees. Apparently, we can conclude that here, for this specific task, the number of trees starting from 50 up to 200 has a negligible impact, while the result can be way more pushed toward a better value by increasing the number of the depth of the tree. So how many questions we allow to the tree. And as I said, this means that we have spent part of the optimization problem trying to optimize a parameter that doesn't want to be optimized, actually, or that is negligible for this task, at least in this range. Probably if I would use just one decision tree, I would see an effect, but still I'm wasting some time. This is the confusion matrix. Here there is there should be another cell here. I lost one cell. I will be back. So sorry. Well, in this case, the SVC again, we are declaring and testing the support vector machine. One slightly different thing is the probability here is set to true, because SVM, for how they are being defined, actually they do not produce any possible probability. So there are some tricks to enable this function that basically is perform internally several trains and averaging. It's a trick, but since usually it's helpful to have something like that, it can be done. Again, okay. Here there is the grid search for the sites for the SVM. Here we have the two parameters that I want to optimize, and there is a huge quantity of code that is only for producing this plot, because together with the points I have interpolated the points with an RBF to see where the best solution seems to be. So here I've performed the 15 experiments with the two parameters that I chose to optimize, and again there is some improvement with respect to the random forest, where we saw mostly just one parameter that was helping. Here is slightly different in both senses, but I can do something slightly different. Rather than showing you the random coupling, here I decided to use a library that is called Optuna. It's again explained by Alexandra, not by me, so it's really clear how it works. Basically, it starts by searching random coupling of the values, and then using the Bayesian inference, try to identify portion of the hyperparameter space, that is a funny space, to identify where the best solution should be, are probably there. Actually, it tries to do two things. try to find the region where there should be a good solution, and at the same time, the region where there could be a bad solution. Since the Bayesian logic is quite complex, there could be region that can, in which you can have a bad and a good solution at the same time. So the model avoids those regions, try to find just region where it's supposed to get the best results. So basically, this is done in that way. So I'm creating an objective where I give the two hyperparameters that I want to tune, and I'm saying that is a float, and the range in which they should span. And also here I'm specifying that they usually works in logarithmic scale, because this is the way in which the Bayesian logic will search for that, avoiding just small steps. Again, I have the declaration of the model where C should be CVAL, that is the one suggested by by Optuna, and gamma again is the other one. We were using just RBF and the random state of 42, just in order to be always sure that everything is exactly the same. So I can fit and predict and get back to the F1 score. Again, a huge amount of stuff. And as you can see, the same 15 trial spanned a very, very different region of the hyperparameter space. In some regions where he identified that there were the best solution, he went with more details by selecting more. This is the main difference with respect to the plot that I showed you in the previous case, in which clearly the one is just an interpolation that I did without a Bayesian approach, but it's not so different. So it's exploring differently the hyperparameter space, and it was capable to obtain better results. These are all the scores that we have. The results are slightly better with respect to the grid search, so do not expect major updates, but anything can help. It's always welcome, at least from my side. This is something that I didn't mention it in the previous case, since we want to be sure that we are not selecting a model just because the last digit of the accuracy score is slightly better than the other model. Often is a good idea to change something and perform several training in order to verify if the result is just better because it's one digit, or it's better because it's significant. In this case, since the dataset is really small, this has been done 1,000 times by bootstrapping, so doing the same thing that the random forest do natively, excuse me, not naively. So replacing some of the values with a replacement of the other one. So each one of these 1,000 model has been trained on slightly different training points. And I can, well, those are the best, the absolute best, the average score, the absolute worst, that can clearly help you to choose your model. Or you can also do something more fancy and plot something that has a relation. So you can probably say that the KNN is reasonably performing worse than the other two models. It's not always needed to do that, but it's a good idea if the model does not take months to be trained to perform something like that in order to optimize the score. For what concerns the model interpretation, I mentioned the existence of the random forest feature importance here. And it's something that is obtained by the trained model polling the feature importance. This will give you several several information that you can select. Here I'm selecting only, the top 10, and I can see what are the most important. If you want to know from me what is the meaning of any of this column, I have completely no idea, but I assume that is some kind of dust in the air. So it's the only thing that I know. I don't know if it's reasonable that this is the most important, but it's completely unimportant for what concerns our task. Besides that, there is a library that is called SHAP that performs something slightly more complex. Has several methods for different models. In particular, for what concerns the random forest, is what it does is to going through all the trees, neglecting completely one of the features. So whenever the tree is split according to this feature, it will go in both ways and see what actually changed. It's quite simple to be used to. It's just creating a tree explainer, and it can produce several summary plots. The first of all is this one that is suggesting not only which are the features that are more important, but also what a value does to a prediction on average. This means that a high value of this feature not only is important, but is pushing the model toward in this case, the bad class, while a low value of this feature is pushing the model toward a low probability of this class. And this is quite interesting to be analyzed for several tasks. Besides that, you can also combine this with another feature and see exactly what is, rather than high and low value, what is actually happening with different values of the original feature to the score. So if it's high, it's pushing toward bad in this specific case. If it's low, it's negative, it's pushing away from the classification of bad. Just because I choose to analyze this feature clearly. It can be done for all the features. And this is interesting too, but it can do also something more detailed. It can work on a single prediction. So in this case, for the sample number 0, so since I'm very lazy, the first line of this data set is important because it's the first line. I can see how the different features contributed to the classification as class 0. So this feature in particular, for which the value was this whatever, pushed the probability up to 15%. So I can try to understand for a given point what is the reason for which the specific prediction has been done, and this can be interesting. Clearly, any model is a representation of the world. Doesn't mean that the world is actually that. This is the reason the model shows that way. Does not mean that the reality, but it's the best that we can have. For the regression, I used the one of the feature, and basically well, again, the train split because we changed the label. The regression metrics are being explained. You should cheer Alexandra because she did a great job. So here I'm creating an object that is a regressor, random forest regressor. I give you the number of estimator, the depth, the random state, and so on and so forth. I fit and I predict the regression, and then I can just plot the results. For regression, I'm afraid that the best scenario will always be a diagonal result. And despite having the axis scaled by log or or linearly. This is probably the most important plot that you always will have for regression. There is nothing more fancy than that. Now, I want you to do an exercise. Here there is in the bottom of the notebook, there is a dataset, the breast cancer dataset. It's a classification dataset. And here in the final cell of the notebook is loading all the data. So you should have all that you need. So you have the features and the labels, and you should be able to split the data, scale the feature, set up a grid search, or you can test independently some values as you prefer. And you should also be able to produce a confusion matrix. In the worst case scenario, even if you didn't list anything, just by cut and paste something from the previous cells. So it should be quite easy to be done. And we have, I don't know, how many times we have? Yeah, you should be able to do that. And clearly, if you have any possible problem, me and Ilenia, Giuseppe, and so on, we can help you with the code, but should be quite straightforward, I hope. If you finish it, try to make the problem more complex or try another model. If you have, besides that, if you have any question, please. But it's mostly things that we already seen. It's just the way in which the code is written now.
Stefano, maybe it's a naive question. It's just because I was wondering, I was digging through the code, and the plot that you showed about the contour map, the heat map between the two parameters, the hyperparameters of the support vector machine, to choose what is the best for the one of the indicator. I don't remember, it's F1.
F1, yeah, problem.
Can you show that? Because I'm not sure I understood how to read that plot. Naively, I was going to the most bluish part,
Yes.
so the highest.
Yes.
But then in the text later, it says that the best solution is at 10 for C, for the X values, and 0.1 for the Y value. That doesn't correspond to the bluish, the highest value.
This one is done on the validation set, and the final result is no. This is on the trial. I don't remember. Sorry.
No, I see. But this is generally done on the validation set, as you were saying, right?
Yeah.
And
yeah, but the final value that is prompted at the end is the one on the test set.
I see. So this is the difference. So can we?
But just the final value. In fact, if I don't remember wrongly, it's in the plot you see something above 90s, and in the final result is 88 or something like that.
Yeah, I was just wondering because there was this like incongruence that I missed. Okay, thank you.